So after going through rectilinear motion in the previous video, in this video we are going to see general motion of a particle. So this is how the author starts the discussion. When a particle moves in 2 or 3 dimensional space. In rectilinear motion we saw movement in 1 dimensional space, and that too, that was a straight line. But now we are going to consider general motion. So the motion can be restricted in a plane, or it can be any type of motion in 3 dimensional space, that means this space. Then its position, the particle's position can be described by its vector displacement r vector, which is the position vector of the particle from an origin O that is fixed in a rigid reference frame F. Whether F itself is moving or not is irrelevant here. R will be measured relative to O. Now let us try to see why we need a reference frame F and not just a point O that we are going to treat as origin. Say this is our particle P moving in 3 dimensional space along some path, and let this be the rigid reference frame F in which some point O is rigidly fixed, which we are treating as the origin. And with respect to the origin, we are considering the position vector of the particle P, and we are calling that R. Now the question is this: what is a rigid frame? That is one question, and the second will be why we need a rigid frame. Is just O not enough? So the author first defines a rigid reference frame. A rigid reference frame is essentially a rigid body. We already know what a rigid body is from the previous video. It's a collection of particles where the particles do not change relative position with respect to one another, such that the particles of this rigid body can be labeled to create reference points, such as the Earth. The Earth is actually not a rigid body, but as we discussed previously, nothing is perfectly rigid. But for most purposes, solids are, you know what type of solids I am talking about, they can be considered as rigid bodies. But now the question is this: why do we need a rigid reference frame? And the reason is this: relative to a single particle, the only thing that can be specified is distance from the particle. Alright, but then how is that a problem? The problem is this: you imagine for a moment that the rigid reference frame F is not present here, and you only have the point O. Now the particle P is moving. Now you imagine yourself moving with P. Say P is some kind of vehicle and you are moving. How do you track your motion? And how do you even know that you are moving? By looking outside, looking out the window. Motion only makes sense when there is a way of measuring it, and more fundamentally when there is a way of seeing that you are moving, and that always involves looking at something with respect to which you are moving, right? There should always be a reference. Now why can that reference not be a single point? Well, it can be, but then you will lose something. Because if you are only able to see how far you are from that single point, then you lose direction. Say you are moving along a circle with that single point as the center. Keep in mind that single point is just a single point. It's not a rigid body. It does not have any composition, and it's not an extended object, so that when you go around it, you can see that it's rotating. It's rotating from your point of view means you are rotating around it. That thing is not available anymore because that's a single point. And that is why we lose the ability to track that type of motion. That is why only a single point is not enough. We need a rigid frame of reference, an extended body actually. That is why we need this. And the author writes next, because of this, but relative to a rigid body, you can specify both distance and direction. Thus, the value of any vector quantity can be specified relative to f, because distance and direction correspond to magnitude and direction. Only distance is not enough, that only gives you magnitude. In particular, if we label some particle O as the origin, as we have done here, particle of what? Particle of that rigid reference frame, which is a rigid body. Then we can specify the position of any point in space, such as this arbitrary position of the particle, by its position vector relative to f and the origin. And this is usually done by introducing a Cartesian coordinate system in f, and that too it can be done in infinitely many different ways. So you have options. According to how you need your coordinate system, you can choose it. Imagine that f is extended by a set of 3 mutually orthogonal planes. This type of thing you see when you look at a corner of some room, ordinary room in your house, where 3 mutually orthogonal planes meet. So, such planes have been rigidly embedded in f, and the point where they meet is that O, the origin. Then you already know how to calculate the coordinates of P with respect to such a system, because the intersections of these planes are going to be your 3 axes, which are also mutually orthogonal. And the coordinates x, y and z of P are then signed distances of P from these planes. Signed distances because they can be negatable. So depending on where the point P is, in which octant it lies. So let O be the origin of this coordinate system, and I hat, j hat and k hat be its unit vectors. You understand what these unit vectors mean. I mean, those 3 orthogonal planes intersect in some straight lines. Those straight lines are the axes, and these are unit vectors in the positive directions of those axes. So now you can see them here. I hat, j hat and k hat. They are mutually orthogonal. We can then conveniently refer to the frame f together with this embedded coordinate system O, x, y, z. So this O is the origin and these are the 3 axes with this notation as f, O, I hat, j hat, k hat. And then we have the definition of general velocity and acceleration. 3D velocity and acceleration, the text calls it so, but in 3D, 2D is also included. That's a special case. And the definition is actually very simple. The velocity is a vector v, and the acceleration is also a vector a of the particle p are defined by these equations. V is the time derivative of that displacement vector or position vector, and acceleration is the time derivative of the velocity vector. You can see that some general directions of these 2 vectors have also been shown. This is how it appears in the text. And we will see later, not today but in the next video, that this V is along that unit tangent vector. That is why we studied those things in the beginning. The direction of acceleration vector is more complicated. It's not along the unit normal vector, okay. It is not always perpendicular to velocity. We will see in which way it directs. Now before we see any example of this general motion, velocity and acceleration of such motion, let us also see what the connection of this thing is with rectilinear case. That means, how are velocity and acceleration as defined in this definition related to velocity and acceleration that we defined in the previous video, where the motion is along a straight line. For the rectilinear case, there was a diagram like this, where the motion is along this line, not necessarily in this direction, but it is confined to be on the line. So P is the particle which is moving in whatever manner it's moving. And in fact, we saw one example also where the position of P or the displacement of P from O was given to be this, where T is time. X is given as a function of time. And according to our definitions of velocity and acceleration, they were just this. V is the time derivative of x and acceleration is the time derivative of v. That's just it. But how are these things linked to these things? This is how, through this equation. Here only x is given, but actually this is also given. I mean, if you really consider the displacement as a vector, then the position vector of the point P or the particle P with respect to O itself is given. We just did not write the I hat. You remember in the previous video I actually explicitly mentioned this. And then if you apply this definition itself to this, then what happens? You are differentiating r vector with respect to time. Now, as your particle P moves on this line, I hat does not change. I hat just stays I hat pointing in this same positive x direction and also maintaining its unit magnitude. So that is why you only have to differentiate this x. Actually, there is a second term also where you write plus x times the derivative of I hat with respect to t, which however is the zero vector. So that part vanishes. So you are left with only this. If you go to the previous video thumbnail, there in fact I have used this notation where I made this red to indicate that it's hidden. This however is just our ordinary velocity, I mean the way we defined it back there. So that's why this is v I hat. Similarly, this acceleration is nothing but old acceleration times I hat. If you go back to the old definitions of this v and a, there you will see this phrase in the direction, in the positive x direction. That fact indicates that we have I hat with these things, if we consider them as vectors, which they actually are. So that is the connection with the rectilinear case of this general case. Next we have this example 2.4. Relative to some reference frame FOIJK, some reference frame, the position vector of a particle P at time t is given by this. Vector r is 2t squared minus 3 I hat plus 4t plus 4 j hat plus t cube plus 2t squared k hat. We then have to find three things. Number one, find the distance OP when t is equal to 0. That means we have to find the distance of P from the origin O when the journey started. Number two, we have to find the velocity when time is 1, and number 3, the acceleration when time is 2. The solution to part 1 is pretty easy. We first calculate r of 0. Don't get confused by this notation, okay? We don't write t here, but actually r is a function of t. So in that sense I am using the notation here. That means I am evaluating r when t is equal to 0. And that of course you just put t equal to 0 here, you get minus 3 I hat plus 4 j hat. This part vanishes. And then you just calculate the magnitude of this. I should have written r of 0 here, but I ran out of space. So that's how you get OP, and that is 5. Then part 2 is velocity, for which you have to differentiate this with respect to time. This is that r vector, I accidentally erased it. But anyway, before you write this though, you need to mention that because in our frame of reference, the vectors I hat, j hat and k hat do not change with time. So their time derivatives are 0. And then you do the differentiation. So that means you just have to differentiate the coefficient functions, which are ordinary real valued functions of t. So the derivative of this with respect to t is 4t. When you differentiate this, you get 4, and this one gives you 3t square plus 4t. And then you have to calculate the velocity when the time is 1 in some unit. So you calculate v of 1. Just like r is a function of t, v is also a function of t, and you can see that here. So you calculate v of 1, and this is what you get: 4i hat plus 4j hat plus 7k hat. Whatever vector this is the velocity vector exactly when the time is 1. And finally, part 3, where we calculate acceleration. To do that, you differentiate velocity with respect to time, again keeping in mind that I hat, j hat and k hat are constant. So you differentiate 4t with respect to t, you get 4. So 4i hat, this one vanishes because there is no t, this one is constant, and this one becomes 3t squared becomes 6t because 2 comes down, and 4t becomes 4. So this is your acceleration as a function of time again, and that then you evaluate when the time is 2. So that way you get 4i hat plus 16k hat. The video ends here. Next week we are going to see the directions in which these two vectors, velocity and acceleration, point. As we discussed today itself briefly in the beginning, you will see that the velocity points in the direction of the unit tangent vector to the path along which the particle is moving at some given instant. Acceleration, however, points in a direction which is not along the unit normal vector, but it will be a combination of the tangent and the normal vectors. We will see what the coefficients in that linear combination are, what those quantities are, and then if time permits, I think we will have more time. I mean, besides seeing that, we will have time to do something else also. There we will see possibly, I think, if I am remembering correctly, uniform circular motion, and then we have other things also.